post hoc I'm referring to is going to be speaking later today. Carmelo Camilleri has really pushed the work in our group forward very quickly. So I'm going to talk about another way we can use remotely sensed ET. You've heard a lot about using it for monitoring water use. I'll be talking about some applications in monitoring drought. And I think remotely sensed ET gives us a really good early warning signal of incipient drought. And we had a good opportunity to test this out this year. We've done most of this drought work at coarse spatial scales, so I'll be talking about kind of larger scale than Landsat, but the uses for this type of application, I think, even become more critical at the Landsat scale when you can look at stress in individual fields. So, as I said, great year to, not a great year for agriculture in the Corn Belt, central United States, and parts of the western United States, but a good opportunity to test capabilities of some drought monitoring tools. We watched this year as severe to exceptional drought conditions rapidly enveloped much of the United States. Because this drought came on so quickly with so little forewarning, it's kind of earned the dubious title of a flash drought situation, and analogous to flash flooding conditions. You can see the impact of this flash drought on, I'm not as tall as Rick is, on crop conditions. This is corn grown in the state of Illinois. This is survey data collected by the National Ag Statistics Survey, collected by trained observers in the field. They're reporting on crop conditions on a weekly time step on a county level scale. And as you can see here, is there the top button is a pointer?
Yes. There's another pointer right there to your right.
Right here?
Yes.
How do you make this one go? Oh, that's great. Okay, which is better. The corn condition started to decay almost upon emergence in May, and it decaying rapidly, kind of bottoming out at the end of July, when less than 10% of all corn grown in Illinois was deemed to be in good to excellent condition, which is just awful. You can compare that to prior years. This is 2011. Wasn't a great year for corn growing either, but a whole lot better than 2012, and to crop conditions in prior years as well. In this year, we had kind of a conjunction of below normal, this isn't even worth pointing this at, below normal precipitation over the Midwest, parts of the western states, coinciding with a lingering heat wave that really drove some strong evaporative fluxes, rapidly depleting moisture reserves in the topsoil, in the upper couple centimeters of the soil profile through direct evaporation off the soil, also depleting moisture reserves in the root zone that should have been there available for crop uptake later in the season. Where the low precip and the heat wave signals intersect kind of define the core of where the drought developed this year. This is a remote sensing drought index based on satellite-derived estimates of evapotranspiration. It's looking at temporal anomalies and the ratio of actual to potential ETs. So red areas here experienced much below normal evaporative fluxes over a 3-month period ending in July, signaling severe depletion in the soil moisture reserves. So initially there was very high evaporative flux, and then it just bottomed out until we got something like this. These ET models that we use to compute evapotranspiration using satellite imagery typically consider all the major drivers of flash drought. They consider hot air temperatures, hot surface temperatures. They also considered wind conditions. The stronger the winds, the faster the evaporative losses. So oftentimes these flash droughts are accompanied by very strong extended wind periods. They consider solar radiation. If you have a long period of cloudless days, you have a lot of sunshine available to evaporate the water. All these factors are accommodated in these ET models. So I would make the claim that ET-based drought indicators are uniquely well suited for capturing these rapid onset drought events. Now there's a lot of ways to map evapotranspiration over large areas. I'm going to contrast two typical ways, a water balance approach versus the energy balance approach we use in thermal remote sensing. In the water balance approach, and this is used very commonly in lots of land surface models, you're assuming you know the precipitation very accurately, and then you use some physically based land surface equations to compute the flows of waters through the land surface system. And this is very useful. You get consistent estimates of a lot of components of the hydrologic budget. But the challenge is that this kind of approach requires a specification of a whole lot of parameters over the land surface to get this to work right. You need to know a lot about the soil properties, or soil moisture holding capacity, the infiltration conductance. You need to know a lot about the vegetation. What's the rooting depth? What's their sensitivity to moisture deficiencies in the root zone to get that evapotranspiration right? These are parameters that are very difficult to specify with any accuracy over large areas. Also, you need to know precip very accurately. And that's not such a problem here in the US, where we have Doppler radars, we have rain gauges for correction. It's more of a challenge in some other parts of the world where we don't have the dense ground-based meteorological infrastructure we have here. So in contrast, there's another approach. We use an energy balance approach to estimating the evapotranspiration. And in this approach, we need to know very little about the soil properties. And very importantly, we don't need to know the precipitation. In this approach, the evaporative fluxes are being diagnosed from the land surface temperatures that we observe from the satellite systems that have thermal imaging systems on them. So we know evaporation cools things off. It cools the soil down as water evaporates directly from the soil. It cools the plants down as they're transpiring water. So in this approach, the question we're posing is, if we know how much energy is being put into the system from the sun, from the atmosphere, how much water must be evaporating to keep the soil and the vegetation at the temperatures that we observe? And we can answer that question if we have a temperature-based surface energy balance algorithm. So if you look at this, you can see there are two very independent ways at getting at the same quantity, evapotranspiration. Water balance versus energy balance require different inputs, precipitation, surface temperature, and have different requirements about our knowledge, our a priori knowledge about the land surface. I would make the claim that it is very valuable to run both of these types of systems in parallel. You have two independent estimates of the same quantity. If they're giving you the same answer, you have a lot more confidence in emerging drought signals, especially if they're rapid onset events. Now, we do have a lot of thermal sensors available to us to do this ET mapping, giving you some examples at the global to continental scales. We can use these weather satellites, these geostationary satellites. Give us excellent time information. We can get a snapshot of land surface temperature every 15 minutes. But the resolution is pretty coarse. We can't see individual farm fields at that scale. So, so here we have a map. Here we have that doesn't work at all. We have a map over the United States that's composed of data collected by the GOES East and GOES West weather satellites. We can zoom in, little higher spatial resolution using data from the MODIS thermal sensors at a kilometer spatial resolution. We can start to see some kind of general hydrologic patterns across the landscape, enhanced ET along the river basins. But Landsat, especially from somebody who works for the USDA, is critical for so many water management applications, because we can start, of course, to resolve evaporative fluxes from individual farm fields. So if you put this all together, though, you could imagine in the future kind of a Google Earth for water resource monitoring, where we can step back and look at water use and drought patterns globally or at the continental scale using one set of satellites, and then zoom in on areas of specific interest and look in very detail at the water use and stress patterns over that region. Once we build up these time series of evaporative maps at these different spatial scales, we can start computing temporal anomalies. And that's when we move from monitoring water use into monitoring drought, which is always primarily based on looking at anomalies in hydrologic parameters. And that's what I'm going to be talking about now. So this, in the lower right-hand corner is this evaporative stress index that I mentioned earlier. It's sampling temporal anomalies in evaporative flux. Red indicates lower than normal moisture conditions. On the upper right, we have the U.S. Drought Monitor. Upper left, the classifications. This is for the growing season of 27. And a soil moisture anomaly in the upper right. And that was computed by a land surface model based on the water balance approach, where they used the precipitation, they computed the evapotranspiration. You can compare that to the energy balance approach using the surface temperature data. The patterns are pretty comparable, and that's a good thing. We're getting the same patterns from two different, completely independent approaches. Convergence of evidence means that we're pretty confident in these drought patterns then. We can get a whole lot higher spatial resolution when we use the temperature data to make these maps. We don't have precip information at this kind of spatial scale, and we certainly don't have it at the field-to-field scale. We can never do this type of analysis through water balance at a field scale, but we can do it with the satellite imaging. This is another soil moisture variable retrieved by microwave, passive microwave remote sensing, another kind of popular technique for getting at soil moisture conditions, but we completely lose the signal of the drought in the southeast in the microwaves. This is because microwaves are strongly absorbed by water that's contained in the vegetative canopy. So you're losing the signal in the southeast where there's very dense vegetation, but we're seeing it very strongly in the thermal wave band because of this impact of moisture deficiencies on surface temperature. The canopy is stopping its transpiration, it's stopping its evaporative cooling, the canopy temperatures are elevated, so we get a strong thermal signal of the drought in that region. Oh, just a bunch of maps of drought mapped with different techniques. I won't get into this. Looking at monthly evolution in the drought patterns, we see good correspondence too. The ESI is shown there, a water balance estimate of soil moisture anomalies in the column next to it. You can see again the strong spatial correspondence between these independent techniques at getting the drought impacts. Now let's get to 2012, and this is what things look like for 2012. We have the U.S. Drought Monitor drought classifications in the first column, this evaporative stress index based on surface temperature in the second column. And in the third column is a drought index that's based on anomalies in a vegetation index. Essentially, how much more or less green vegetation was present at any given time than is normally there. You can see that about in May, we started seeing a pretty strong signal in the evaporative stress index over where the core of the drought was later to develop. The drought monitor classification didn't really catch up until July. Couple months later, the vegetation index-based drought index didn't show a strong signal in this region until May either. But remember, in the corn condition plots, that corn condition was starting to suffer right from May. And we feel like we're getting some advanced warning of this deteriorating crop condition in this thermal signal. Vegetation index, that's not going to reveal anything until the crops are actually damaged and they're dying back. But the stress impacts on the vegetation first manifest themselves in this thermal signal. And so that's why I would make the claim that surface temperature is a really useful early warning signal of these, especially in these flash drought situations. I'm not going to get into this. We're putting out these drought assessments at the continental scale. Again, these are based on data from the GOES geostationary satellites on a website. They're updated every day through the growing season. And you can look at these if you want to. You can compare with other drought classifications, drought monitor classifications, standardized precipitation index. You can lock the two frames together and click through time and see how the drought patterns have changed. And I have kind of a movie of this. I'm not sure if I can activate this or how. Maybe you could click, just put the little hand over the movie and click. Because kind of interesting to see. I think you get a visual impression of sometimes of the early warning capacity in the thermal signal. 2010 wasn't a terribly interesting year for drought, but this is where the movie starts, except for later in the year we had a high sitting over the southeast, and we had some drought conditions that are showing up first in the evaporative stress index and then later in the drought monitor. So that was 2010. 2011, the big story was down in Texas when the fields were just burning up early in the season, and ranchers were trying to figure out where they're going to get their supplemental field. Probably have to buy it from Idaho or someplace that wasn't so drought affected that year. We're getting good temporal correspondence with the thermal-based evaporative stress index and the patterns that were developing and being reported in the U.S. drought monitor that year. And now into 2012. Started out, the big concern at the beginning of 2012 was down in Georgia, but starting in May, we started seeing something weird going on in the central U.S. And I was getting a little concerned about evaporative stress index, like this must be some processing anomaly, but sure enough, later on, a huge bullseye developed over that same region. So you may have to get us out of this. If you can click over in the blue area here, maybe that'll stop it.
Couple minutes, please.
Yes. So I'll start to wrap up here. I've shown you a lot of analysis at the continental scale that we can do with these geostationary satellites. But the value may be in doing these types of analyses at finer spatial scales. And I can envision a multi-scale drought monitoring system where we make these continental scale maps, we use them to identify drought-affected regions, and then we make these higher resolution assessments of stress anomalies using systems like MODIS and Landsat. And here's a couple different examples. At the Landsat scale, we can start getting at stress signatures at the scale of individual farm fields, and that's going to be critical for improving our yield estimates. Different crops show different stress temporal patterns. Different crops are differently affected by moisture deficiencies at different parts of the year. So we really want to resolve the stress patterns on corn from that of adjacent soybeans to really improve the yield estimates. And this is where we want to go in part with our work with the Landsat science team coming up. We've applied some of these techniques over some other parts of the world that are more data sparse, where we don't have a lot of ground-based data. I'll just briefly show you some applications over North Africa. This is a ET map that we've made with the Meteosat geostationary satellite at 3 kilometer spatial resolution. And we're applying these same drought monitoring tools in this region too. On the left is ET, on the right is this normalized ET over PET index that we use for the drought monitoring. And if we apply that for 2011, remember there was the big famine in the Horn of Africa. We see a bullseye of very low evaporative water consumption, kind of coinciding with the hot spot of the famine in 2011. So we feel like these tools have applications not only in the US but also globally. So thank you very much.